Chapter 15 focuses on acids and bases. I'm going to start by talking about characteristics of the acids and bases and eventually get into how to calculate pH and pOH of strong acids and bases, and also weak acids and weak bases. And this is where equilibrium comes into play when we're calculating our pH. As always, there's some suggested problems for you at the end of the book, end of the chapter, that you can use to help determine your understanding of these concepts. Let's start by talking a little bit about acids. And we're pretty familiar with acids that occur in our food. They taste sour, so the citric acid in citrus fruits, or the malic acid in other fruits like grapes and apples. They have the ability to dissolve lots of different metals, not all metals, which we'll learn about, but many metals, and they can neutralize bases. So in the past, we've talked about how acids start with hydrogen. We're going to expand our definition in this chapter, but our acids that we see in this slide, so we still start with H, and these H's at the beginning are the acidic hydrogens. There is a polyatomic ion, so in nitric acid, our polyatomic ion is nitrate, and then that hydrogen is what makes it acidic. In sulfuric acid, our polyatomic ion is the sulfate, and the hydrogen makes it acidic. Those polyatomic ions are negatively charged, so they pull the electron density away from the hydrogens, making them able to dissociate away from the ion. Same with the citric acid and the malic acid, but our polyatomic ion gets a little bit larger in these cases. Now, hydrochloric acid is a strong acid, and this is made of just hydrogen and a group 7 nonmetal, in this case chlorine. And so again, we have the H plus and the Cl minus, and the Cl minus, the electronegativity pulls the electron density away from that hydrogen, making it able to dissociate. Now, we're going to look at carboxylic acids. So carboxylic acids have a group, a functional group that is COO. Okay, again, this pulls the electron density away from the hydrogen, allowing it to easily dissociate. So when we see these COOH, that is what we refer to as a carboxylic acid group, and this does make it an acid when we see this group. Only the H in the carboxylic acid group is acidic. So here's a list of some common acids and where we use them. So hydrochloric acid, this is the stomach acid that helps to break down food. We use it for lots of things like cleaning and also digesting our food. Sulfuric acid can be used in fertilizers and explosives. This is also the acid in the car batteries that you use as an electrolyte. And nitric acid gets used in lots of places like fertilizer and explosives as well. Acetic acid, this is vinegar. So vinegar is a very dilute solution of acetic acid. And again, this is a carboxylic acid group. So COOH is what makes this hydrogen acidic. Got citric acid, carbonic acid, that's in carbonated beverages. Okay, it's a combination of carbon dioxide when it mixed with water produces carbonic acid. Hydrofluoric acid, this is for metal cleaning. It also can etch glass. So hydrofluoric acid cannot be stored in glass because it actually does etch the glass. And phosphoric acid gets used frequently for biological buffering and also food preservation and fertilizer manufacturing. If we look at bases, bases have slightly different properties. So they taste bitter. So these are things like alkaloids. So they're typically alkaline and can be poisonous, which is part of the reason why they taste bitter to us, so that we don't ingest them. They do feel slippery. If you get them on your skin, the bases start to feel very slippery. And they do have the ability to neutralize acids. These bases are found in many of the cleaning products that we use. So sodium hydroxide we use in the lab quite frequently. It can be used to make soaps and petroleum processing. Potassium hydroxide, so notice here we have the OH. The OH minus is a previous definition that we used for bases. And so these are cotton processing for potassium hydroxide. Soap production can also be used in batteries. We're going to expand our definition just a little bit to include other types of bases. So you'll notice that we no longer have the OH minus present, but sodium bicarbonate, this is baking soda. Okay, and so we use this for lots of things like antacids. Sodium carbonate gets used to make glass and soap. Okay, it works quite well, but again, we do not have that OH minus, and we'll talk more about these definitions later in the chapter. Ammonium, or ammonia, NH3, is also a base, and that is because it can accept a hydrogen, and it gets used in fertilizers, detergents, and lots of other places that we can use ammonia. So the Arrhenius theory, this is the definition you're most familiar with. And an Arrhenius acid produces H+, and an Arrhenius base produces OH-. So this is the familiar definition that we're used to. So HCl would dissociate into H+, making an acid, Cl- as the anion. NaOH would dissociate into Na+, OH-, which makes it a base. Just to clarify a topic in chemistry that gets used kind of interchangeably, you'll see frequently H+ being written in a chemical reaction or in the dissociation reactions we just looked at, where we get H+ and Cl-. Just so you're aware, H+ is very, very reactive. They do not exist in water on their own, although we write them in chemical reactions. They are just protons. Doesn't have any electrons around that nucleus of the hydrogen. So once they are dissociated, they actually react with water molecules and form a complex. And this complex is what we call the hydronium ion. So when H+ reacts with water, we get H3O+. And so frequently chemists use H+ and H3O+ interchangeably. So if you see H+, it really does exist as H3O+ in the water, but we frequently use either or both of these representations. So if we look at an Arrhenius acid, when it reacts with a Arrhenius base, we get an acid plus the base gives us a generic salt. It doesn't have to be NaCl, but it's going to be a cation and an anion combined, and typically these are aqueous solutions. They dissolve in water. And the other result is, because we have H+ and OH-, that produces water as a liquid in the chemical reaction.